Good.
We are again investigating the work energy theorem, this time with friction, in which we're using this block sent down the ramp, which has a certain amount of friction preventing it from accelerating freely. And what we're trying to figure out is what's the work done by friction as it travels down the ramp. So we're going to use the same theorem, force times your net force times your distance equals your mass times your final velocity squared divided by 2, given a new set of standards. Our mass is 0.139 kilograms. Gravity is still negative 9.8 meters per second. Theta this time was 19 degrees, and our delta x remains the same at half a meter. So we can set up our diagram here to see all the forces acting on all the relevant forces acting on our block. Gravity is pulling down with 1.362 newtons, which means the force pulling it down the ramp is 0.443 newtons, mg sine theta. But we also have this frictional force that we don't know, preventing it from accelerating as it would if it was free. So to find our work done by friction, going back where your work is the changing kinetic energy, it's going to be our ideal kinetic energy I, which would be our block traveling in a frictionless environment, minus our actual kinetic energy, which is what we're going to measure. So to find our KEI, ideal kinetic energy, we set up this function to find our ideal velocity, which is 1.79 meters per second, and then again thanks to the magic of math. More math magic, and we have kinetic energy ideal equals 0.223 joules. So hang on to that. When we send the block down and through the photo gate, we measure that our actual velocity is 0.719 meters per second, considerably slower than the 1.79 here. So we do more math magic with that, and we find that actual kinetic energy is equal to 0.036 joules. Then we set up this formula up here, again, with the actual values, and find that the work done by friction is 0.187 joules. Jeremiah again says, math works.